So bombs are a fun way to talk about conservation of momentum. We've got a bomb that is sitting at rest on a table. So he's sitting, oh, let's just make it kind of right here. We've got a bomb. It explodes into 4 pieces of equal mass. The first piece travels to the south at a velocity of 55 meters per second. So after, we're going to go straight down this way at 55 meters per second. The second piece travels to the west with a velocity of 80. Oops. 80 meters per second. And the third piece travels with a velocity to the west of north. So this is going to be north, so it's going to go this way at 30 degrees at 40 meters per second. Now we can draw in that axis. Let's go ahead and do those real quick. So here is our y-axis here. This is our north axis. So this is going to be 40 degrees, 30 degrees west of north. And then our x-axis, let's do this. That's a nice circle. So here's our x-axis. On the top, it's a nice circle. Okay, so we want to know what is the velocity of the fourth piece. Now, hopefully, we kind of have an idea of what's sort of going on here. We're talking about this conservation of momentum, conservation of something, and we have a piece going this way, a piece going this way, and a piece going this way. So hopefully, we kind of see that our last piece is going to go probably somewhere off this direction. We don't really know that for sure, but we're just going to kind of estimate to start with. And maybe when we get our math done, it's going to be something completely different. But our fourth piece is going to go off, maybe a little bit more down. I don't know, we'll see. So here's what we know. We know that momentum is conserved, and we know that our initial momentum is going to be 0. So our initial momentum is going to be equal to the momentum of all 4 pieces added together. So let's just take this for right now. Let's start with that. Okay. So our initial momentum is our bomb, and it's just sitting there, and that's going to be 0. And we have 4 other pieces that are going off in all different directions. And so we are going to have to resolve these into vectors, since we're not, it's not going to be a perfect explosion this way and this way. So we've got some vectors that are going on here. So we're really interested here, here's P4. We're really interested in what is the momentum in the y direction of this fourth one and the momentum in the x direction of this fourth one. Okay. So let's start with x, shall we? X marks the spot. So we're going to start with our x momentum. So momentum in the x direction, the total momentum in the x direction is going to be equal to the x of, well, let's just label these, shall we? Let's call this one 1, and this one 2, and this one 3. And then that'll be 4. So let's look at P1. P1 is going only in the y direction. So the momentum in the x direction of 1 is 0, because it's not going anywhere. The momentum in the x direction of P2 is going to be, well, just the total momentum of P2, because it's only going in the x direction. And then we're going to have to resolve this. So this is our x of 3, and this is our y of 3 here. So we have components on part 3. So the x that's going this direction is the opposite. So that's going to be the opposite is sine. The sine, so the momentum of 3 times the sine of 30 degrees. And then this is going to be plus the x momentum of 4. Okay. Now we know that we also know that up here there is no momentum initially in any direction from our bomb. So we're solving for this right here. So px4 is going to be equal to the momentum of 2 plus the momentum of 3 times the sine of its angle. So from here, we don't really know the masses. It doesn't give us any masses, but what we do know is that they're all equal masses. So it doesn't really matter what the mass is. We can say that the mass of each one is 1, because now it's just going to be proportional. It doesn't matter if the mass is 1 or 1,000 or 423. All of those will end up being proportional, since mass will all cancel out from each one of those. So we can just say, let's just say it's 1, just to make it nice and easy. So P2 is moving at 80 degrees. Now you do need to make sure, let's just define this way as our negative direction and this way as our positive direction. All right, so this is going to be a negative 80 meters per second times our 1 mass. Okay, and then plus this is also going to be negative. So we're going to have negative 40 meters per second times the sine of 30 degrees. And then the sine of 30 is 0.5. So when we multiply all, oops, this is x4. So when we multiply all of this out, the momentum in the x direction for part 4 is going to be 100 meters per second. This is actually negative because we moved it over, didn't we? Make sure your negatives are all in a row, times 1. So what we end up with is the x component is going to be 100 meters per second in the x direction. Okay, so this right here is going to be 100 meters per second. If I could keep my negatives straight, that would be helpful. Alrighty, so let's do y. So y, same thing. The momentum in the total momentum in the y direction is going to be equal to P1y plus P2y plus P3y plus P4y. Okay, and again, this is 0 because it's not moving at all before it starts. Now P1 is only going down, so it's only in the y direction. So this is just the total momentum of part 1. Part 2 is moving in only the x direction, so it's going to be 0. Part 3 has a component to it, so that is going to be the momentum of 3 times the cosine of 30 degrees plus the momentum of 4. All right. So now we're trying to find this. So again, let's make sure our negatives are correct. There we go. It's going to be equal to the momentum of 1. So 55 meters per second times our 1 mass plus 0 plus the 40 meters per second times the cosine of 30 degrees. Oh, now this one will be negative. After my negatives here, this one's negative, but this one's going to be positive because we're going up. So what we end up with, gosh, I wish my negatives were good. So we're going to punch this in. We get 34.6 plus 35. So we're going to, or minus 35. So 55. Gosh, I can't talk this morning. So P4y is going to be equal to, this is a 5 that I can't tell because I've screwed it all up. So this is negative 55 plus 35-ish. So P4 is going to be a positive 20 meters per second times our one mass. And so we're going to have positive 20 kilogram meters per second. So this up here would actually also have, it's too early. This is momentum since we multiplied it by mass. Okay. So to find the total momentum of part 4, we have a triangle, right? So this up here will be 20 meters per second. There. So really, in order to find the momentum, we're just going to do Pythagorean. So 20, kilogram meters per second squared plus 100 kilogram meters per second is going to be 20 squared plus 100 squared will be 102. Okay. So that gives us the magnitude of our momentum, and now we want to find our angle. And so again, pick your favorite function. We can just use tangent over here. So the tangent of theta will be the opposite over adjacent. So 20 divided by 100. And then the inverse of the tangent will give us 11 degrees. And this is going to be 11 degrees north of east. So our momentum we can write as 102 kilogram meters per second at 11 degrees north of east. So we had a pretty good estimation here, a little bit too big on our angle, but we kind of actually noticed that at the beginning. So really what I want you to see here, see how this is all going this way? That would mean we would have to have something going pretty quickly in this direction to balance all of these other things on this side out.